Hello. So we are going to be working on problem 4. So this is a big one. We are putting it all together. So we're going to have, we're going to find the market equilibrium price for a given good X. Here we're going to have consumers and producers. So there are 200 consumers of type A, where these consumers of type A have preferences that are perfect complements. So it's the minimum of 3x and y. And type A consumers have income of 12. There are also 500 consumers of type B with preferences U of B, which are Cobb-Douglas preferences. So it's 3x to the 1/3, y to the 2/3. Type B consumers have an income of 20. The price of y is normalized to 1, and the price of x is p. Okay, so for 4a, we're going to find the demand function for a consumer of type A and the demand function of a consumer of type B. And we're going to do these for good X. So A, UA of XY is the min of 3x and y. Okay, so this is a perfect complements utility function. The optimal consumption bundle is going to be the one which has 3x equal to y. All right, so this gives us our optimality condition. We kind of just know this off the bat. So what happens here is we plug this into the budget constraint. So again, the income of type A is 12. So we have MA is equal to P times X plus 1 times Y. All right, substituting this in, we have that 12 is equal to P times X plus 3X. So I'm substituting in Y is equal to 3X. All right, so this simplifies to X times 3 plus P is equal to 12, which is satisfied when X is equal to 12 over 3 plus P. So we don't need to find the one for Y here. We're only concerned with the demand for X. Okay. So now what we're going to do is we're going to find the demand function for a consumer of type B. Okay. So we want to find the demand for type B. We have that the utility of agent B for goods X and Y is equal to 3 X to the 1/3, Y to the 2/3. I'm going to check that. Yep. All right. So what we do here, this is Cobb-Douglas. It'll have an interior solution, and then the interior solution is going to be characterized by tangency. So we're going to have the MRS between X and Y is equal to P over 1. This is what we need. This is Px over Py. Okay, so first we'll compute the MRS. So this is the partial derivative of u with respect to x divided by the partial derivative of u with respect to y. So this is just 3 times 1/3 x to the negative 1/3 y to the 2/3, here's this here, over 3 times 2/3 times x to the 1/3, y to the negative 1/3. All right, just do some simplifying here. We get this is y over 2x. Okay, so this is the marginal rate of substitution. Now we set MRS xy equal to p over 1. So this implies that we have y over 2x is equal to p. In other words, we have that y is equal to 2p times x. All right, so just like we did previously, plug this into the budget constraint. Okay, so the income of consumer B is 20. So MB is equal to 20. This implies we have 20 is equal to P times X plus 1 times Y, and Y is 2P times X. So we have 20 is equal to 3px. In other words, x is equal to 20 over 3p. So I'm just going to summarize. The demand for x for type A was 12 over 3 plus p. The demand for consumer type B is going to be 20 over 3p. All right. So this is our demand for good x. Now for part, I'm gonna do a little check mark. Now for part B, we want to find the market demand function. So we did the hard part. We found the demand function for each type of consumer. Now we just have to note that there are 200 consumers of type A and 500 consumers of type B. So the total market demand is just going to be 500 times this. Oh, sorry, no, 200 times this, because there are 200 type A. So there's 200 of these, and there's 500 of these. So I just add those up and weigh by the number of people that are of that type. So B, total demand, so we have 200 times 12 over 3 plus p plus 500 times 20 over 3p. Nothing more than that. So this is the market demand. I'm just going to write equals QD of P. All right, and give it a nice little color. It shall be green. All right, so this is how you find total market demand. You just take the demand of each type of consumer and weigh by the number of consumers that are of that type. All right, so another part done. Now what we do is we want to consider the supply side. So firms have a cost function. C of Q is equal to 100 plus 3Q squared. And the fixed cost, this 100, is avoidable. So we are asked to find what the minimum average cost is. So what we're doing here is we're finding the minimum average avoidable cost. So we have C of Q. It was 100 plus 3Q squared. All right. 100 is an avoidable fixed cost. So the average avoidable cost, like this is all avoidable cost. So the average avoidable cost, like it's asking us to find the minimum of the average avoidable cost. So we have to first find the average avoidable cost. So it's going to be 100 over Q plus 3Q. What I'm doing is I'm just saying, okay, this is my avoidable cost. I'm going to divide this by Q to get the average avoidable cost. And I get this. Graphically, what we're looking for, we want to find graphically, I think I already did this in a previous problem, but I just want to really emphasize, we have this average avoidable cost function, which looks like this. Not like that. So it's going to look something like this. The idea is we want to find the point at which this is minimized. That point, this Q, E, is the efficient scale. All right, and this, just to be clear, this orange line is the AAC, it's a function of Q. This is Q, this is C. All right, so we want to find this point where the derivative is equal to 0, and then this will tell us the point where the AAC is minimized. So this is what we want to find, just graphically. So this means we just find the efficient scale, set the derivative of AAC equal to 0, and that'll give us the efficient scale. Then we plug the efficient scale back into the AAC. So to minimize this function, we take the first derivative. So this is negative 100 over Q squared plus 3. We want to set this equal to 0 to find the minimum. So what this means is we have 3 is equal to 100 over Q squared. I'm just going to write to find min. All right, so this means we have Q squared is equal to 100 over 3. In other words, Q is equal to 10 over the square root of 3. Right, so this is the efficient scale. Now, we have that the AAC min is just going to be the average avoidable cost at the quantity which minimizes it, so at the efficient scale. All right, so we just plug this into the average avoidable cost. We get 100 over 10 over root 3 plus 3 times 10 over root 3. Okay, let's do some algebra wizardry here. So this is 10 over 1 over root 3 plus 30 what's the best way to simplify this? Yeah, okay, I'm going to leave it like 3 times 10 over root 3. So what we can do here is I have a fraction on the bottom here. So I can just flip this and multiply it by the reciprocal. So I get 10 root 3 plus Yeah, okay, so as an aside, 3 over the square root of 3 is just 3, it's just root 3 squared over root 3, which is just root 3. Nice little simplification here. How does this help us? Well, this just becomes this one on the right becomes root 3 times 10. So this whole thing is just 20 times the square root of 3. A nice, relatively nice number. So this is going to be an important number because it determines basically when the firm is going to produce or not. We'll get to that in a second. This one's going to be red. No, I don't quite like that shade. Let's do blue. All right. Found the minimum average cost. Now we're going to do equilibrium stuff. So what is the equilibrium price that emerges in this market? And what is the equilibrium quantity with free entry? Okay. So if there's free entry, basically this is saying like assume there's free entry, perfect competition. We're going to look at the equilibrium price that emerges. How do we do that? Well, I'm going to give myself more space here. I always get excited about equilibrium, so there's going to be an exclamation point here. So we're finding long-run equilibrium. In the long run, we will have, with, free entry, price equal to the AAC min. So this is going to be 20 root 3. And then quantity. What we're going to do is plug PLR star into the quantity demanded, P. So this will give us the equilibrium quantity in the long run. So QLR star. So this is saying the equilibrium quantity in the long run is going to be the demand function evaluated at the long run price. So this is going to be, as we found earlier, we have that this is like 200 times 12 over 3 plus P. So PLR star plus 500 times 20 over 3 PLR star. Okay, so we're going to plug in. PLR star is equal to 20 root 3. So QLR star is equal to 20 200 times 12 over 3 plus 20 root 3 plus 500 times 20 over 3 times 20 root 3. There's a nice cancellation with the 20s here. Not much else really nicely cancels. This is going to be approximately like 160. All right, so this is the long-run market equilibrium. Here we just saw that the price in the long run is just going to be the average avoidable cost. Firms are going to enter until prices get driven down to this. The quantity demanded in equilibrium is just going to be the quantity demanded at this market price, and that's going to be 160. That's the quantity demanded in equilibrium in the long run. So now, just going back, do our little check mark. Now we're just changing the environment a little bit. There are 800 consumers of type B. There are no consumers of type A. We want to find what the market price is and what the equilibrium quantity of good X that is produced and sold. All right, very similar setup. Here we just have a different number of consumers. 0 type A, 800 type B. All right, so this doesn't change the cost function for the firm. The firm, nothing about the firm's problem changes. The only thing that changes is market demand. So the quantity demanded at a given price P is now just going to be 800 times the demand for B. And the demand for B was 20 over 3 times P. So this is 16,000 divided by 3P, I think. Yeah. So, just to, in equilibrium, P star, long run, again, is just AAC min. That part doesn't change, because again, nothing about the firm's problem changed. So this is 20 root 3. This is the long run equilibrium price. Nothing about that changes. What we do now is we find the new demand in equilibrium. So we have a different demand function. So we just plug the AAC min, we plug the long run price in, and we solve for demand. So this is going to be 16,000 divided by 3 times 20 root 3. And just kind of, this is, I think it's around like 154. Yeah, that's what the solutions on Canvas say. All right, so the long run price, or the long run quantity, QD, or I'll just say Q long run, because this is the quantity supplied and demanded, is equal to approximately 154. All right. So we just found the long run price and quantity when we had a different demand structure. So when we had 800 type B, 0 type A. All right. So that is problem 4. Thanks for watching.